Today we're going to talk about chi-square analysis, and we're going to use chi-square analysis to evaluate the influence of chance on genetic data. Consider for a moment the coin toss. If you were to flip a coin 10 times, how many times do you think you'd get tails? Probably you predicted 5 times, because each time you flip a coin, you have a 50-50 chance of getting tails. But now I want you to actually do this. Take out a coin and flip it 10 times. Your classmates should do it too. And when you're done, consolidate your number of tails onto a table. Pause me and start me up again when you've finished. Chances are your table looked something like this. Some students might have gotten tails 3 times. Like student 2 here. Some students might have gotten tails 7 times, like student 3. Students might have actually gotten 5 times. And there's this whole range of numbers. But when you averaged it out, you probably ended up somewhere around 4.3, maybe you had 6.1, but someplace around 5. What I want you to think about right now is, how do you account for the difference in trials? What would happen if you increase the number of times that you flip that coin? Pause me and press play after you've answered these questions. After thinking about it, I'm guessing that you would have accounted for the differences in these trials because of chance. You said, each time I flip a coin, I have a 50-50 chance of getting tails, which means I could get tails 10 times in a row. But if I flipped my coin 100 times, I'd probably get even closer to 50%. And if I flipped my coin 1,000 times, I'd probably get even closer to 50%. This is all due to chance deviation. These are chance events that are subject to random fluctuation. There's chance deviation in genetics. Segregation, how alleles separate from each other and end up in different gametes. Independent assortment, fertilization, which gametes end up coming together. We try to account for this in things like a Punnett square or in an egg sperm chart, where we talk about all the different ways that different alleles could come together. But like anything else, this is subject to chance deviation or random fluctuations. Now, the larger the number of crosses we do, we expect to see smaller differences, a smaller impact of chance. Let's look at an example. If you cross 2 hybrid tall plants and produce 100 offspring, predict how many tall and how many short we would get. Pause me and press play when you're ready. After crossing 2 hybrid tall plants, big D, little d, big D, little d, chances are you expected to see 75% of those would be tall and 25% of those would be short. So your predicted number, 75% of 100, is 75, and 25% of 100 is 25. Your predicted number would be 75 tall plants and 25 short plants. But in reality, if you took those 2 tall plants and crossed them, you wouldn't get exactly 75 and 25. Probably you'd get a different number. What if your actual number was 77 and 23? Does that seem close enough? Maybe. But how do we decide how close is close enough? That's where chi-square analysis comes into play. The null hypothesis is we assume that the data will fit a given ratio. So it assumes there's no real difference, and any apparent differences are just due to chance. It's not something weird, something different going on. For example, in this situation, the null hypothesis would be that the difference between the predicted number of tall and short plants and the actual number was because of chance, not because there's something different genetically going on. Chi-square analysis is used to test how well the data fits the null hypothesis. Now this is where the language gets a little bit funky here, so I want you to pay close attention. If the observed deviation can be attributed to chance, then we say the null hypothesis will fail to be rejected. That's kind of strange, so think about that again. So that means we are totally fine with this. Any differences are due to chance. So then we would say the null hypothesis fails to be rejected. But if the observed deviation can't be attributed to chance, meaning there's something else going on here, then we say that the null hypothesis will be rejected. This is the equation that we're going to use for chi-square analysis. Notice that D stands for the deviation, the difference between the observed and the expected, and E is our expected. We're also going to use something called degrees of freedom here, because chi-square analysis might talk about a lot of different phenotypes or categories, and the more categories that we have, or more phenotypes that we have, the more deviation we can expect. So to figure out our degrees of freedom, we take n, or the number of categories, or in genetics, the number of phenotypes, and we subtract 1. So in the example we were just doing where we had tall and short plants, there were 2 different phenotypes, so we would say 2 minus 1 gives us 1 in terms of our degrees of freedom. Now let's try an example together. If you have 2 hybrid tall plants, big D, little d, that are crossed, and they produce 740 tall and 260 short plants, can the deviation in this observation be explained by chance? Well, the first thing you need to do is figure out what our expected should be. So, if you've got 2 hybrid tall plants and they're crossed, you would expect to see 3 talls and 1 short. Or if we're doing a lot more than 4, we would expect to see 75% tall and 25% short plants. Well, in this situation, we don't just have 4 plants, we have a lot more than 4 plants. So, we're going to organize this into a table. These tables will first have our expected ratio. We would say 3/4 of the plants should be tall and 1/4 of the plant should be short. Then in the table, put your observed in. We actually have 740 tall plants and 260 short plants. The next thing I'd ask you to do is to add up all of the plants that you observed. So in this case, 740 and 260 gives you 1,000 plants. Now we know our total number of plants. Then take your expected ratio and multiply it by your total number of plants to get our actual expected number of plants. So if we have 1,000 plants and 3/4 or 75% of them are supposed to be tall, then we would expect to see 750 tall plants. In the same sense, 1/4 times 1,000 would give us 250. We would expect to see 250 short plants. Then you're going to go ahead and say, what's our deviation? Our deviation is our observed minus our expected, so 740 minus 750. So in this case, it's -10. And for the short plants, it would be 260 minus 250 gives us a +10. Then you're going to square this deviation. So -10 times -10 is 100 here, and +10 times +10 is 100 here. Then you're going to take this deviation squared and divide it by your expected. So in this case, we're going to take 100 and divide it by 750 and get 0.13. We'll do the same thing here. 100 divided by the expected 250 gives us 0.40. Now we take all of our chi-square values here and we add them up from the different categories and we get 0.13 and 0.40, or a 0.53 as our chi-squared value. Now we have to figure out what to do with this information. So far we figured out our chi-square value is 0.53. Our degrees of freedom, we look at our categories, phenotypes. We can have either tall or short plants. So that's 2 categories minus 1, because degrees of freedom is your number of categories minus 1. So 2 minus 1 is 1. So now I'm going to take that information and I'm going to use it in our chi-square value table. So start with your degrees of freedom. We're at 1, so we're going to look in this row. We look for the number that's closest to our chi-square value. As we go along, it's going to be somewhere in here, probably closest to this 0.46, because 0.53 is closest to 0.46. So we'll say our probability is around 0.5. Now, we have to decide where to draw our line in the sand. In this probability and chi-square table, we drew our line in the sand right here, meaning anything in this darker blue area fails to reject the null hypothesis. That's fine. We're okay with that. These differences can be attributed to chance. However, things that fall in this light blue area, we're saying, no, that is not good enough. There's something else going on here. We are going to reject our null hypothesis and say we have to look for another example. It's not just chance that's causing our prediction to be different from our observed. So in this situation, this 0.53 that fell right around here, our probability of 0.5 is close enough. It falls in this dark blue area. So we say it fails to reject the null hypothesis. And you would write that down. And then you would write this. You would say, so the observed deviation can be observed by chance.